All right, welcome everybody. Tonight we're going to be talking about this paper here, Reinforcing Multi-Turn Reasoning in LLM Agents via Turn-Level Credit Assignment. If that's a mouthful that doesn't mean much to you, don't worry, I'll explain it. It is a smaller paper from a smaller group that didn't make too many waves, but I think caught my eye because I like reinforcement learning and I've worked with it a lot. And this is a very difficult problem that they're proposing a very simple solution for, and that's kind of why I got fascinated by it. Uh, my name's Keith Chester. Who am I? Well, I am the person that typically runs the paper club. I'll be presenting tonight. I have a master's degree in robotics engineering, so I like robots. You can reach me on the Discord on SDX at Halfshell. Feel free to ping me if you have any questions, follow-up stuff, or you're building something cool and just want to chat about it. I'm great for that. You can reach me at Keith at halfshell.ai. I also have halfshell.ai, which is a blog post where I routinely post about tech. That QR code will take you to it. Also, I have a blog post about this paper already up, and as soon as this video hits YouTube, that will also be accessible from there. And you can see some of my prior talks and some other stuff I've worked on there as well. So we're going to start by building a foundation. Quick show of hands, who here has worked with reinforcement learning before? One back there, over there. Okay. What did you build? Anything interesting?
Mostly schoolwork. I haven't built anything outside of the classroom.
Okay, so typical reinforcement.
Very simple
Game agents. Any deep learning, deep reinforcement learning, or just basic like MDPs? Sorry. Okay. Donkey car. Okay, Donkey Car, great project if anybody's seen that before. It's a self-driving remote control car. There is a group in San Diego that races them every week or every so often, I think. So definitely a fun little project. My experience with reinforcement learning was, yes, a lot of coursework and very much on robotics, because right now a lot of the cutting edge in robotics is built upon that reinforcement learning and starting to implement a lot of the transformers and vision language action models. We're not going to go too much into that tonight, but we are going to be talking about the basics of reinforcement learning. So who here has ever heard me talk about reinforcement learning before? What do I commonly say about reinforcement learning? Yes, if you can avoid doing it, don't do it. And why is that the case? Well, the problem is that reinforcement learning is a bit of a pain in the butt. I use it a lot, but only when I have to. And why is that the case? Well, it's difficult to use, it's unstable, and it's different from your typical machine learning, where you'd say using convolutional neural network to do the good old cats and dogs project, right? Why is that the case? Well, it's because when you are working in machine learning, you basically have a direct mathematical relationship between what you wanted the model to do and what it actually did based on the input. In the end, you have basically one connected net that is a series of mathematical equations from input to output, and as a result, we can, using some algorithm or technique or process, backpropagate the error back through the model to adjust it slightly for what happened. That doesn't work in reinforcement learning. Specifically, reinforcement learning is a set of processes, algorithms, techniques to model situations and agents to get around situations where that's not true. A good example, and we will go into more example later, is let's talk about, say, a robot that pitches a baseball to a batter, right? I can create a mathematical relationship to track the ball, sure, but what about the limbs of the robot, the air resistance, where the batter is standing at that particular moment? Maybe you can picture a set of mathematical relationships for all of what I'm talking about, but it gets really unwieldy really quickly. And that's what reinforcement learning is trying to solve. It's trying to create agents that can deal with that incredible complexity where we can't find that link, that mathematical link between the two things. So this makes it really difficult. And one of the prime examples that of the difficulty is assigning credit. Now, this is what the paper talks about in depth. And a couple of you asked me to kind of clarify what they meant by that. So first, we're going to talk about designing rewards. When you are trying to assign credit to something, sometimes you might think, okay, well, I'm going to design a reward system for this agent as it kind of interacts in the environment as I train it. And this is often called reward engineering, or designing rewards, or sometimes curricula, where you're trying to create a series of scaled rewards that slowly teach the agent a certain way. These are all valid things you can do, But models are really good at cheating, and often best intentioned approaches to this fail. And a great example is from OpenAI many, many years ago. Here's a little clip from OpenAI.
So this is an AI made by OpenAI. It's playing a game called Coast Runners, which is actually a racing game. They trained it on the score, which you probably can't see down here. It's currently 1,000. What the system learned is that if it goes around in a circle here and crashes into everything and catches fire, these little turbo pickups, they respawn at just the right rate, that if it just flings itself around in a circle, it can pick up the turbo, and that gives you a few points every time you do that. And it turns out that this is a much better way of getting points than actually racing around the track.
So that's one example. Two more examples I'll give is one is a person that created a system that could play Nintendo games was playing Tetris, and at the hardest difficulty, the model just paused the game right before it died and refused to unpause. And so it never lost. Something that I did once is I created a model that would run through a scientific simulation of the traffic of Chicago using something called Sumo, which is a thing researchers use to model traffic. I sent an agent to try and figure out better traffic timings for a Chicago area with realistic traffic. And sure enough, I started getting amazing results. But when I looked at it, I realized that the agent realized that these drivers, unlike real Chicago drivers, are polite and won't get into car crashes without certain simulation settings turned on, and just turned off all traffic lights throughout the city because that was the most optimal way. And that's not ideal. And this is what happens a lot when you do this kind of reward engineering. You have to try and figure out how is the model going to cheat. And very often you find that it's going to discover whatever bug or method it can find to optimize, it's going to do it. Now, let's see if I can. Okay, so the result is that sometimes the environment or the state or whatever you're trying to simulate is way too complicated, or we want to avoid getting caught in this loop of reward and curricular engineering that we just want to sidestep entirely. This is why a lot of reinforcement learning is focused on something called sparse rewards. This is basically 0 if you failed, 1 if you passed. Nothing else, no in-betweens. This is extremely easy to do because, well, if we're throwing a baseball, did the baseball go over the plate and was it a strike? Great, 1. If it wasn't, 0. But you can obviously see where this gets really difficult because there is a lot of room between monumental failure and actually succeeding once. And this is where reinforcement learning kind of gets a lot of its sample inefficiency, where it takes forever to get the model to do simple things because we don't have a way to communicate to the agent that you're doing something slightly wrong, and we're far away from the harder task. So assigning credit is hard though, and this is a series of slides that I used about a year ago when I was talking about decision transformers at like maybe the 3rd ever paper club, but I'm going to reuse them because I'm a little lazy. Let's say we have this super contrived example of just a grid-based world, a robot that can go up and over, a cake if it can reach it, and a bear trap, which is not good for the robot. So contrived, but it's pretty telling, and it'll help us kind of build a basis. So anytime the robot moves in a discrete step, I'm going to use the word step a lot. The paper uses the word turn. They are used interchangeably for the most part in reinforcement learning. So if I say step, I should probably be saying turn, and vice versa. A state is what the world is and the observations thereof, sometimes not the observations and extra hidden state stuff, but the state is what the world is at that particular time step. So if this world would change as the robot moved, the state would change as it stepped. An action is whatever the model did. A start to finish, be it into the bear trap, timeout, or into the cake, or off the world's edge, that's an episode. And the series of decisions and actions that the agent took, so every observation, every state, and every action taken throughout the entire episode is your trajectory. Whenever you hear these terms, this is what it's talking about. Any questions on this? Yes.
The step turn thing, the turn is probably because they were doing a conversation.
Yes. Yes, but you do see turn and other stuff too with board games because reinforcement learning uses a lot of board games too. Yeah.
But you're doing an actual
step. Yeah. So I tend to think of it as step because remember my background is robotics. So we break continuous time into like discrete time steps, and we have the robot trying to do these large continuous tasks. But when you're doing turn-based stuff like the conversation or board game, you're going to see it mentioned turn. It's the same thing, right? So Any questions about this definition before I move on? All right, the next thing I'm going to define here is Q and V. Who knows what these are? Without looking at the slide, that's obviously explaining what they are. Okay, you know what Q is? Very, very close. I would say, yeah, that's pretty much right. That's what you were going to say? Yeah. So sometimes, in fact, I would say the first year that I was playing with reinforcement learning, I always got these confused. What the hell is the difference and why does it matter? Well, first, I'll define. Q of SA is the reward of a state given an action, and V of S is the expected reward of being in a state. What is this actually saying? This is essentially saying you were in a state and you took this action and this is what you got. You were in a state and I expect you to make this much off of it. That will be important later, trust me. Okay, so we have a robot and we know we want to move. Unfortunately, it chose wrong, but how do we assign credit for the stuff that it did? Yes? The live stream is dead because of YouTube issues. Okay, so how do we assign credit for what the robot is doing in order to train our agent, right? How do we score each state action combo for our training? So we could have designed a set of points for every single move, but that's exhausting, and we just talked about earlier how that can lead into a trap. So there's something really common called the Bellman equation, which is just a way to assign value to Q. It is important to know, but only loosely associated to what we're going with, but I still wanted to cover it because it kind of sets you up for what we're going to cover later. This is a really complicated mathematical equation, but it's actually really easy. What it's saying is the value of the state action combo that you formed here is equal to the value earned for the whole trajectory, discounted based off of how far back it is. So if we were to say, oh, hey, I wrote it down. Value of a state given an action is equal to the sum of all rewards in cumulative future states multiplied by decaying factor. The decaying factor is gamma. Why do we need gamma here? What is it actually doing? Well, whenever you have that question, set it to 1. So if we had 2 cakes and we had a gamma set to 1, this is the resulting Q value of every single square. Now, one thing is immediately obvious. It does not matter which cake you go to. So the agent might learn to take this route instead of this route. They are equally good according to the agent. But if we were to instead apply, this is reward shaping that I was talking about earlier, if we instead apply a 0.9 to it, we have differing values for each path that it could take. And this cake is now better because to take the green path would take a lower QA score because we are decaying the Q value at each square. And then this agent would be just as simple as for all the paths that you see, just take the highest scoring one. And the robot will now always go to the cake. Pretty simple. Questions about that before I move on? Okay? All right, so defining responsibility, that was kind of a contrived example, but here's a real one. Who here plays chess? A couple of people? Okay, this is made in 3. I'll give you a second. That's the end state, so that's kind of the cheat. Anybody? Okay. Those moves here. Queen, check, forces the king down. Queen, check, covered by the knight, forces the king down. Queen, check here, takes pawn, covered by the knight, checkmate. Right? It's really obvious to us right now which moves of all the moves available to the agent are going to lead to victory and why they're valuable. These 3 moves, right? The problem is that this game started like this. So how do I assign credit to the first pawn move, which was, I believe this game was an E2, E4, but I don't remember. It was a chess puzzle off chess.com. So that's really difficult. And you can see in chess, it explodes out. And now if we start talking about real life applications for like robots, it's going to be even more complicated. So yeah, what about a robot tossing a ball into a basketball hoop? Again, you can engineer a whole bunch of different ways to create rewards based off the arc of the basketball and whether it gripped it correctly and whether the ball went higher than the net or approached the net and if it bounced off the backboard or not. But in the end, you're doing a lot of work for a learning agent that's going to be just very complicated. And you're going to want to instead reach for a sparse reward. But now I can't reward the robot for something as simple as putting the hand near the ball. And now it's going to take millions and millions and millions of training steps for it just to learn, oh, hey, maybe I could pick this ball up before we even get to remotely close to throwing it correctly. So turn level credit is kind of a proposed approach that might be able to solve this. So they basically said, we're going to think of the agents as Markov decision processes, MDPs. And all you need to know about MDPs, because this is more of their justification for why they were doing stuff the way they were doing, is that it is an agent that has a transition function for a given environment to try and find the optimal reward at any given state. That's a very wide definition. It's because a lot of things can be defined as MDPs and structured as that. But yes, they are basically just using this as a justification of looking at agents at individual steps for an agentic workflow as individual MDPs. So we're going to talk about GRPO, which is where the meat of the paper starts to be. I have talked about GRPO as a presentation for the Paper Club before. We are going to cover it here as well, but if you want more information and you want to see a video or read a blog post that goes into this in depth, more depth than I'm about to go into, that's the link right there. It'll take you to my blog where that's the thing. These slides will be on the Discord immediately after the talk as well. And again, if you found the #AI site, this video and this post is up there. Links for those articles are also there. So, GRPO. Who here has worked with GRPO before? No one? Who here has worked with PPO? PPO? What should you build with it? Oh, the RC card. Yeah, okay. That makes perfect sense. So PPO was a 2017 OpenAI reinforcement learning algorithm, which is what powered the original ChatGPT instruct training reasoning, a whole bunch of other discoveries throughout robotics and reinforcement learning. It's a very powerful algorithm, but it had certain issues when we came to language models. And GRPO is a methodology for adjusting PPO, kind of like a next level, specifically for language models, that's really good about training it for reasoning and other instruct-based stuff. It's what DeepSeek uses, and in fact, I think most of the model providers are using something very similar to this, but DeepSeek is using it for their instruct models right now. The goal is, and you can't really see my model color, for some reason purple doesn't come through there, but you take a prompt, you take the model that you're actively training, and you have the model output G responses. DeepSeek, I believe, does 8 at a time. Each of these responses then go into the GRPO algorithm, which I'm going to jump into in a second, and basically get graded together in such a way that their combined scores is more telling than an individual step. They are basically being judged by accuracy and format most commonly. We're going to tweak that a little bit when we get to the MTGRPO, but that's the basic idea. Take a model, produce a bunch of responses, judge them somehow, and then use the GRPO algorithm to kind of bring the adjustment back to the model based off of how you did it. Okay, so this really simple math equation is GRPO, and it's kind of self-explanatory, so I'm just going to go right past it. Or we're going to spend the next 10 minutes explaining it. So this, whenever I get math, especially in a paper, I'm not the best at understanding this stuff, and my eyes tend to roll back to the back of my head, and I pass out, and like I didn't learn anything from the paper then. And it's problematic because a lot of us here are programmers, right? We have learned throughout programming that we should be coding in the most descriptive, verbose way possible in order to make sure that anyone that reads our code can understand what we're trying to accomplish. This means documenting things, variable names, that's not just X underscore I, right? It's variable names that make sense, that kind of convey a purpose. Mathematics says, screw that, we're going to be as concise as humanly possible, and then a few degrees more. This has always created a disconnect for me. So I have a certain method for teaching math in these paper clubs, and it takes hours and hours and hours to do. So I created an AI agent to do that for me. So I'm just going to quickly advertise. This is eli5equation.com, where you paste a picture of an equation. It will automatically convert it to LaTeX for you. You paste in as much context as possible. I just pasted the whole paper. And then you hit explain equation, and then it generates this stuff for you with complete explanations with color coding. This saves me so many hours. It still takes a while to build these slides with this stuff, but my God, does that help. So eli5equation.com. If you ever use it, let me know. Happy to hear that that might be helping people out there. So back to this equation. We're going to learn how all this works. So first part is the objective function. That's going to be this part right here, all right? And I'm going to remember this diagram right here. So you can't see because of the coloration, and that sucks. So I'm going to have to say it out loud. But this is basically saying JGRPO, which is the objective function, which is basically the loss function in reinforcement learning land, where you see objective function. Think of it as a loss function. Sometimes you have to do the negative of it because you're maximizing rewards versus minimizing error or loss. Your objective function for the parameter weights of your model is equal to the expectation of Q. This basically says Q at P of Q, then a set of O of I of G, and then policy pi of old. Now, wherever you see pi in reinforcement learning, that's your policy. That's basically what is the set of rules or weights that define what the agent does. Now, that's still a mouthful and doesn't really make much sense. So let's walk through it again, but this time with the explanation. This is saying sample a query from a collection of prompts. Hey, here's our prompt. We're going to sample that query from it, and we're going to generate a set of responses to it, creating a set of G outputs using the old policy. Then take the average, here's our old policy, then take the average, which is what expectation actually means, fancy word for just take the average. Take the average of its scores over many iterations and use that to iteratively improve our weights, which is the part you can't see. That seems pretty straightforward and kind of describes what we saw here. That is, again, just this top line, and this line is essentially an expansion of that and how you would actually do it mathematically. So let's dive into that. Can you see all this? So far, yes. Okay. Phew. All right. So again, we take the average, summation 1 over G. Whenever you see that, that means take the average of the probability ratio, which I'll describe in a second, times the advantage. You do some min and clip stuff, and then we have a KL divergence term at the end. And this part that you can't see, unfortunately, because of this projector is how aggressive are our regions. What is all this saying? Well, first let's talk about probability ratios, and then let's talk about advantages. First, what the hell is a probability ratio? Anyone know this one? You might because you worked with PPO. What this is basically the ratio of the probability that the model would have outputted that answer in the old policy and the probability that it would have done that answer with the new model, with the adjusted weights. Why do we have that? Any takers?
Maximum.
Yes, but we're actually trying to do the opposite of that right now. So what happens is reinforcement learning is famously unstable. It is almost impossible to just one-shot learn something really quickly because of the way all of the algorithms work. So what you end up having to do is you have to find ways to make the training process more reliable, more stable. And the number one way to do that for our current top-of-the-line algorithms is to minimize the update on any individual sample. So what this is saying is find the probability that the new model would have done it and the old model would have done it, and you create a ratio. And you're basically saying if the old model would have very likely have done this, and the new model would have very likely have done this, that's a very small update. So that's perfectly fine. If those instead are very far apart, then we have a very large update and we have a very large ratio that represents that. So now we can mathematically tweak. Yes?
Do you care whether it's greater than 1 or less than 1? In other words, do you care if the new policy is better or worse than the old policy?
No. Now, that's being multiplied by this thing called advantage. Who knows what advantage is? All right. Advantage is one of those ideas that I was so confused the first time I went through PPO, and then once it clicks, it's like, well, why didn't they just say that? It's so much simpler. So advantage, and I told you we'd get back to these terms again, is Q of pi, Q of the policy of the state of action over V of S. Who remembers Q and V? Yeah, Q is?
It's the expected rewards.
It's the reward you did receive for the action.
Rewards.
Yep. So how good was the action we took from this state? How good is the state on average? What does that actually translate to? How much better was this action than average? Or if it wasn't better, how much worse than average was this action? And from that times the ratio, think about what we're putting together there. If the new model is highly probable to do something and it makes it worse, and the old model is not probable to do that, and the making it worse is much worse based off that ratio, you now have a number that is quite large and we can identify it. This clip is basically just saying not above or below 1 minus epsilon, which is just typically like 0.1, so like 0.9 negative and positive. And then here is the probability ratio times that. And you're taking the smaller of the two, either the advantage times the probability ratio or the smaller number times the advantage. And what is all that's basically saying? I want you to figure out how probable it is this update will heavily modify our model, paired with how much of a change or how good of a change it was, paired with a clipped value so we don't make any large updates, and then update this over the collection of stuff in our set. Now, this part at the end, KL divergence, I go into more detail about this at the other talk, but basically it's another penalty term to further penalize you from going later. Now, that advantage, how do you actually calculate that for GRPO? You take the reward for a particular piece being, let's say, the score reward for this particular output across the set that we generate for G responses. You take the score of that, subtract from it the mean of that whole set score, and then you divide it by the standard deviation of that score. This is basically saying, hey, this is how much I expect you to do from that state. That prompt should have a score of about this. This is the mean of it. And you're basically saying how much better or worse is it from the average normalized by the standard deviation. Pretty simple once you start to break it down like that. So, KL divergence, like I said, it's basically a further penalty towards preventing large updates. Some people, when they do GRPO or PPO, do not have this. I have it here because DeepSeek uses it, and a lot of applications that use it now have it. But we're not going to go too much into that. But the goal and the lesson is we are penalizing large changes in policy. Now, this does slow down trading, but it makes it more stable. This was super important for LLMs. So, update its strategy based on how much better an action performed compared to the average, which is the advantage. However, it only makes small, careful adjustments, which is called a trust region, by clipping the size of the update and discouraging any large changes with the KL divergence term, then averages these adjustments over multiple experiences to find the best overall improvement. And that's how DeepSeek trains its reasoning models. But this paper introduces changes to this to try and get away from that trajectory level problem of assigning credit. So this paper, if you see me say GRPO OR later, it's actually just referencing base GRPO as we've covered it. GRPO MR is just kind of a test piece to see if their particular change in training pattern was the key innovation, or if their mathematical trick was the key innovation. Well, that'll make sense in a second. And MT-GRPO is the big deal. This is the big innovation from the paper. This is multi-turn GRPO. So, yes, was there a question?
Those G model outputs, they're all from the same model, just with some temperature, some randomness, or are they?
No, because remember, LLM models are natively random. Because
the temperature is set to non-zero.
Yeah.
And so those are 5 from the same model.
Yep, same model, same weights. We generate a whole bunch of responses from it, and then you rate all of them differently somehow. Depends on what you're doing, and then you use those to do the calculation for advantage.
So you've got the advantage, and then how do you adjust the weights of the model?
So this calculates the objective function, which is then used as a loss, and then you back propagate. Yeah. So remember, whenever you see objective function, it's typically either the loss function or the negative of the loss function with reinforcement learning. Yes.
How does that affect the
Clip is a function that can be have a gradient to it. Yes. I have implemented it by hand because I did not know how to use the PyTorch one. It was painful, but it does work. I have used it. Clip and min are things that you can do, as well as taking the probabilities. I will say, if you're taking the probabilities, or you do start to do this, you end up taking the log of the probabilities and using some mathematical tricks in order to get a smooth gradient. But does anyone understand or not understand the question that he's asking here, which is important for backpropagation? Any action that you take on a deep learning model, any mathematical forward step has to have a back step, meaning it has to have some kind of differentiable gradient that you can calculate easily in order to backprop the values of the error, of your loss. So what he's asking me is, can you do that with CLIP, which is a great question, and the answer is yes. 10H? You could probably do that. I think they use CLIP because it's probably computationally faster. But that's a good question. I do not know the answer of how that would affect this overall. I think you get similar results.
Since it's immediately cut off, you should get something really quickly.
Mm-hmm.
Might like cause not just a saturation, but like
That asymptotic value is causing issues with the actual backpropagation and the training. Yeah, I could see that. Yeah, I do not know the answer to that question, so I would not be shocked if someone actually has done that experiment out there. Look them up and let me know what you find, because that's a good question. Any other questions before I go on to the new GRPOs? Okay, so again, we have trajectory level, which is how stuff is typically done. 0, 1 is pass fail. We basically have some kind of score that we're going to backpropagate against an agent, no matter how many steps it took or what it did. And in turn level is we want to basically try and train the agent on each individual step. Yes. Oh, okay. So how is that actually done? Well, first let's look at how training is typically done on a deep learning model with a trajectory level training. Now remember, this is focused on LLM. So every LLM here is the same model. They use Qwen 2.5 7B. Yes.
Each step now is the chain of thought is one of the steps in the model?
Sort of. Let me walk it through. And if there's still a question, let me know. But just note, these are all the same weight. This is all the same model. Okay? Basically, they're saying we can take LLM agents. Typically, you can picture it like this, where the LLM is asked to perform a step, which could do stuff, could have some kind of output, maybe it calls a tool, but it generates a set of, eventually, somehow, a set of input for the next step, which the model gets fed back. It could be post-tool call, it could be triggering some other agent. Then that does something that goes on for time steps t until you get the step O, which is step output, and then it has an output. So this is all the same model, and we're assuming that somehow the output is fed into it. It might not necessarily be the same output, because it could be a tool call. And it's the output of the tool call that ultimately is put there. But the point is that this is how we could model an agentic workflow that we're trying to train with reinforcement learning. So that resulting output from the step output, step O, we want to calculate the outcome advantage. We just covered how to do that in GRPO, right? And once you have that advantage, you use that to basically go through, calculate your objective function, which you use as your loss, and you backpropagate to the model, right? And you backpropagate to the model. There should only really be one. I guess it's kind of confusing I did multiple, but imagine it's just happening once. You backpropagate the model once across the entire trajectory based off that reward calculated here. Does this make sense? Right. So no matter how many steps it took, no matter where it screwed up or where it succeeded, you have a final outcome score, and you are updating the model based on this. The problem with this approach, yes?
Update, changing weights.
Yes. The problem with this,
You're updating it 5 times identically. You're doing back about 5 times. If there's 5
just once. Like I said, I realized that maybe I should have cut those arrows there. It's all the same model. So this whole process creates one score and one backprop step. Yeah, that's my fault for adding the extra lines there. I should remove that. The problem with this approach is that if you screw up here and you get nowhere near this step here, then this score is going to suck. And that means it's going to take a very long time and a lot of data in order to get the agentic behavior you want if it's a complicated procedure of multiple turns. But we've gotten a lot of success with this. We have reasoning models. We have a lot of very impressive reinforcement learning. But they're saying, what if we could do it more efficiently with multi-turn credit? So let's look at what turn level training would look like. Same setup, Quen 2.5B, 2.5 7B, same model throughout, same weights. Just as before, we execute the model exactly the same way. You have an input all the way to the output step. Nothing changed there. But we now calculate the outcome advantage, which we'll talk about how in a second. We calculate a turn-specific advantage for time step t, all the way back to step 1 and step 0. So we have different advantages for every turn now. We use those advantages to plug into our objective function, and then calculate a new loss for each individual model and backprop across the same model separately for each turn we took. I'll give them a moment to let that set in. Any questions? Yes. We're going to cover that in a minute, but that is kind of the key. In fact, it's one of those things that when I showed my wife it, she's like, really, that's the innovation? She doesn't even do AI. She's like, really, is that simple? I'm like, yeah, thanks, dear.
But it's still the same model each step. So you back propagate 10 times.
Yes.
Back prop, step T, and then back
Yep, we're going to back prop off the outcome advantage. We're going to back prop off of this. We're going to back prop off of that. We're going to back prop off of that.
So does each back prop affect the previous calculated advantage? So like on step T,
No, because all these back propagations happen at once, much like you would calculate for a full rollout or a full epoch. And as these are all calculated, and then as soon as we calculate it, we back prop all of them at once as if it was a large rollout. Yes. Yeah. Yes. So the intermediate output, yeah, the intermediate output could be just the raw output of the model. It could be a tool call that gets modified somehow. There could be some process here that is not part of the model, but we don't care about that. But all we know is that that output somehow controls the input to this guy, which is the same model, which performs the next step, and so on and so forth. A good way to view it would be think of a reasoning model, which would say, okay, I'm going to call Google. Google returns this. I'm going to use this now. I'm going to call my PDF to whatever, to a markdown converter, all the way to, okay, I have all the information. Now I'm going to build a RAG database. Here's your output. Yes. No, but I can see where you're coming from with that. And it is kind of like a weird high-level facsimile of it, isn't it? With the way that they handle gating. Yeah, okay. Inspired? Yeah. Yeah. Really.
Only 3 steps, and it was just reasoning, then search, and then summarization.
Yes.
So it makes it a lot easier just to think about it.
Yep. I wanted to present it as a kind of the way that they were presenting, which is this could work for multiple turns, and I'm going to talk about some of my issues with the paper, which touches upon that in a second. But you, yeah. Great question. So if I was just training, imagine for a second we just had this section here, right? And I was training this model based off of this output, and we did not have the whole agentic thing going. So ignore everything over there. What would happen is we would basically have our prompt input, which would be generated into tokens fed into the model, and this would eventually generate tokens until it generates a stop token, and we would score that somehow. Then when you backpropagate, all those tokens get utilized in the backpropagation to say, okay, this was what you did during the time, which create this essential gradient that we're going to calculate back on, and you get the adjustment to the model, right? The same thing is happening at each step. So the tokens that are input and output here are kind of saved. As we do that, it's kind of saved, it's saved, it's saved. And that's true whether or not you're using this or the other approach. So all those tokens are, and the resulting gradient of the model is being kind of utilized for that backpropagation. Follow? And yeah, so that's actually the origin of why I had different arrows, because you are performing backprop with the tokens from this model for this step, even though it's the same backpropagation adjustment, because you're only using the one error score. It's one of those damn if you do, damn if you don't kind of decisions. All right. So we're here. We talked about this is the approach that we're going to do, but we need to know the mathematics of how to calculate that turn advantage. All right. So this is GRPO-MR, which I'm going to come back to. I'm actually going to skip. I'm going to go right to MTGRPO. This is from the paper. Now, again, they only had 3 steps. So they basically had step 0, step 1, and AI 0 is the same, and the last step. But think of this as this is the turn-based step. This is the final step. So every step prior to the final uses this. Final step uses this. So I'm going to look at the final step first. What does this say? All right. Let's go to colors again. Can you see everything this time? Awesome. All right. The final step is basically saying take the reward that you generate from your output reward. We know how to calculate that, right? Subtract the mean across the group. This is reading just like GRPO because it is. It's essentially the same as the GRPO advantage. Nothing changes for that output. Great. We know how to do that. Up here, we see that this term is right here. So this is basically saying, okay, here's that same term from the GRPO advantage function. This one is saying take the step, that particular turn's reward value, calculate the resulting GRPO advantage for that, the same as we would before, but just for that turn, and add the output reward times lambda. So what's lambda? Well, that is kind of the focus here. That's called a relevance factor. So let's go back to the chart up here. And let's say that this agent right here, we knew, let's just say, for sake of argument, that we knew exactly what this agent was going to do and could judge it accordingly. And we knew exactly what this agent was going to do. And we knew that, like, this is a search agent and this is a RAG agent, and the output is just like find the answer from the resulting output, right? We could say how relevant is the final outcome to the success of this turn? Or was this turn truly affected by the fact that the output was wrong? Because maybe it did the search perfectly fine. And if the output is way off and I'm doing a heavy penalty on it, I'm now telling this model what you did here, I don't want you to do anymore. But we don't want to do that. If it found the search result just fine, we want to continue doing that. So I want to reward the model for those particular actions from that state. That's what that lambda function is essentially saying. It's saying that, hey, I want you to determine as the person training this, how relevant is the output of the answer or the correct move to this particular turn. And what that is doing is essentially acting as a relevance factor. So this is saying the first turn's advantage score is found by normalizing the turn reward against the average turn reward and its variability, same as GRPO, but then you add on the normalized output reward multiplied by its turn-specific ratio of relevance. That's all this is doing. It's really simple once you think about it. It's basically saying you're using GRPO on each of these agents individually and just adding a little bit of extra information of the outcome advantage way downrange in order to train the agents. Lambda in training throughout this paper was fixed, and that is one of the things I am not happy with in this paper. They did only one experiment with Lambda. They set Lambda to 0, saying, okay, every turn is going to be completely isolated of the outcome. And they set it to 1, which means it's basically this turn advantage plus the outcome advantage is fully weighted, which means it can affect it. Having a lambda of 0.2, which is a hyperparameter they just chose, outperformed both of those, which teaches you through an experiment, but not deep enough, I feel like, that, hey, it's better to have some of this, but not all of it, and that's better than none of it.
They didn't have any independent measure of the search result quality. They just assumed that it was 20% of the end result quality.
Yes. Yes. Now these are those things where it's like that's really something that you were clearly budget bound or compute bound. That is something I would love to see more on, and I'm going to talk about that in a bit. But yes, you are correct. So that lambda, they test it. It's better to have it at some value between 0 and 1. It's not good to have it at 0, not good to have it at 1. And this was the kind of the big thing that they discovered. Now, this is super simple, but it ends up working real well. Just so I can cover it, GRPMR is a test version of it that kind of mixes the two ideas. It's when you do a lot of these papers, you end up doing things specifically to test to see which part of your idea was the key element that helps it out. So think of this almost like an ablation study where it's part of the idea implemented to show that you need every part of the MTGRPO idea to get the success, and we'll show that in a minute. But this is basically another thing they did where they said, okay, every turn is going to have a particular reward, which is always equal to this plus that. This is the equivalent of having lambda to 1. And we're going to see how that performs. So what did they do for their actual test? This is where the paper kind of gets a little iffy for me. They permanently did a 2-turn test. They did not do variable, possible, agentic stuff. And they had a hard-coded set of what they call verifiers, which is a programmatic way to determine if the text output of these models did or did not perform a certain way and then assigned a reward score for it. So basically, they had step 1 always be an attempt to get a LLM to call a tool for Wikipedia to search Wikipedia for the answer, right? Then they would take that input and then they would say, okay, given this, output the answer. That's it. That's all they did. The way they did the scoring is if the tool was called successfully and actually had, hit Wikipedia, it got 0.2 points. If the answer was in the search response, just by doing a case-insensitive quick graph match, typical regular expression stuff, if that was inside the Wikipedia answer, then it must have searched right. I'll reward it another 0.2 points that turn. If the resulting turn 2 output was in the correct format, XML, don't know why they liked XML, but they chose it. Give it 0.4 points. And if the answer was present in the output, give it 0.5 points. Unless it got exactly the right answer, everything correct, down to the character, then give it 1. Why do I say those scores? Because all the stuff only makes sense if you know what the scores are. So they use Qwen 2.5 7 billion. Who here has done tool calling implemented on open source models before? Anybody? No. Okay. You? Yeah. How big of a model did you use for your tool calling? It's like 70? Yeah. So getting a 7B model to call tools is extremely difficult. Llama, for instance, recommends that you go to 70B in order to have reliable, repeatable tool calling based off of your prescription of how to call it. I can say from experience this is true. So the fact that they were able to get 100% tool calling correct based off of only, I think it was 250, maybe 300 training steps is actually quite impressive. What this is basically showing you is if they take the base Qwen model, the base model for any model provider is a non-instruct base. It's just a very good language model or completion model. They have the instruct model, this they tested, and then they basically took the base, did their own GRPO, standard edition. The GRPO where they added turn credit, which is essentially the same as lambda equals 1. And then the MTGRPO. So the base model basically could not call the tool except for occasionally. You could somehow occasionally look into it. The search answer rarely did, and then the format it was actually really good at, which kind of makes sense. The completion model first, so it knows how to continue the format. And then an exact match for the answer almost never. And the instruct also did not fare super well. The GRPO reports zeros here because it just could not learn how to utilize the tool. Now this might seem weird to you. Why can the instruct do it, but the GRPO original algorithm not do it? Because they only did like 250, 300 steps of training. This instruct was so many more steps with so much more data. They're training it with just a small fine-tuned data set, a small training agent thing. So this is basically saying that not only do we get better results, but it's way more efficient when we do this. That's what they're kind of promising with this. And then if you see the MTGRPO kind of got really high scores across the board. usually finding the answer more often than not because it's 0.5 or higher. So almost always getting the format right, almost always finding the answer in the search, and always calling the tool, which is actually impressive for such a small model. So if you look at the actual charts, you see this again. You see that over the 300 time steps it was that they trained it, the MTGRPO typically outperforms. If you look at the one where lambda is 1, you see that it usually performs well up until a certain point and you start to get an instability, which is something you see a lot in reinforcement learning. This implies that the turn level stuff where you have lambda equals to a non-0 or 0 to 1 value, so not 0, not 1, some fraction, improves stability throughout training, which is really important inside of reinforcement learning. And you can see LCML tag usage. You can see that across the board. Both models kind of got real good at the format output eventually, but MTGRPO outperformed here as well. And we see that across the final answer presence as well. And in the end, they had a model that would almost always call Wikipedia when you asked it a question and could almost always parse that information to try and find your answer. All right, so normally I'd say, well, what questions do people have in terms of the thing or kind of conversation points? But there's a few things that I kind of feel like we're missing. You touched upon some of them. How applicable is this to non-LLM agent models is one that I'm interested in because remember my background is robotics. I'm very interested to see how this can be applied. That mathematical trick that while we saw it throughout GRPO can really easily be applied to any learning algorithm, and as long as it's multi-turn, which is pretty impressive and meaningful of an idea. Can I dynamically engineer the reward for the use of a GRM? Who knows what a GRM is? I talked about it at a previous paper club. Okay, so this QR code will take you to a link with a talk and article on my blog where I talk about GRMs. It's a generative reward model. It is something that DeepSeek trained, and I talked at length a couple paper clubs ago. It is a model specifically trained to train other models by looking at the prompt and generating a set of deep, detailed scoring rubrics for what to expect from the prompt. And then the model can also judge the responses in such a way, utilizing that rubric to find out how the model did to kind of replace human raters. It sounds really complicated, but basically all you have to think about it is that it is a model that's specifically good at figuring out, given the problem at hand, what aspects of an answer are valuable, by how much, and based on the answer to that, how would I rate this? That is what a GRM is. So I'm kind of fascinated by the idea of they had these hard-coded verifiers with these hard-coded hyperparameters that they chose for the individual scores. What if we plugged in a GRM to this? Could you then suddenly start to apply this to all these different kind of use cases for an agent fine-tune and get a really complicated and multi-domain agent out of it? And also, what are the limits to multiple tasks at varying steps? We saw it across three steps here, start to finish. Why not n steps? Why not 9? Why not 11? Is there a point where this stops working and that kind of feedback really suffers? Likewise, you brought up the lambda. They hard-coded it to 0.2. Why is that something that's always hard-coded? Can we experiment more with varying lambdas based off the importance of either the importance of the step towards the potential outcome, which again can be managed by a GRM or another agent or critic, or maybe we can do it decaying based off the length of time before the answer, such that if it's a 21-step process, the first step probably was not the point that you screwed up the most, or maybe it was, and as a result, maybe it shouldn't be affected as much as the 18th step by the outcome reward. All things that I wanted to ask at the end of the paper. The reason this paper caught my eye is because I'm really into reinforcement learning, and I think it kind of proposed a really simple idea that's potentially really powerful. I'm really looking forward to other people picking up the work here to the point that I'm even tempted to try and do the implementation of the GRM into this kind of training to see if you can get a really advanced agent model there. So, any questions for me across anything that was discussed, any discussion points people want to talk about, hit me. All right, you first.
Policy, that's deterministic, or is there ever like some stochastic?
So when you are doing agents, the policy can be either stochastic or deterministic. When you're talking about LLM agents, the policy is always stochastic. The policy, when talking about agents and models in reinforcement learning, refers to the weights of the model and what the model actually does. Make sense?
But is there any
I mean, yeah, yes, because when you're talking about the policy and you're doing the math of the objective function, it is essentially the input and output of the PDF that's going there. When you're looking at the probability ratio, you're actually looking at the log probabilities of what the agent would have done there. Okay? Now, I will say that one addition to your question is that PPO and GRPO are only for stochastic policies, but this idea and reinforcement learning can work with deterministic policies. Right? But if you're using GRPO, it has to be a stochastic policy. I am unaware of any PPO offshoot that uses deterministic policies. Any other questions? There's other hands up. Yes.
Yeah, I have a question about robotics. So, for I guess it would be dependent on the particular job. What would you turns?
Great question.
Where you could apply this turn-based?
I think there's a couple ways that we could possibly see it. One thing I'm going to say is that the way that a lot of modern robotics works, especially a lot of the new AI stuff, is you're using something called a VLA. Rarely is it something like a sensorial motor model where sensor input goes right into a model and motor output comes right out. Instead, it's a VLA that essentially acts as like a router, which then eventually tells the robot to call certain functions within it. Those functions can be hard-coded the old-fashioned way, or utilize like old control algorithms to basically tell the robot, I want you to go to this spot over here in the kitchen, and it'll just do it with the standard robotics stuff we were utilizing prior to all this AI stuff. And then it utilizes additional calls from that router-like calling to call individual specially trained agents for that task. So imagine that if I'm a robot and I'm in the kitchen and I'm told I want you to clean up the mess, the first thing the VLA does is say, okay, I need to find the mess. So I'm just going to look around, which is hard coded. Like, okay, I'm going to spin around, use my computer vision to identify what a mess could be with modern vision language models. And then once it identifies it, it'll say, I'm going to move up to it. Again, that's hard coded. But then it's going to trigger something like, okay, I'm going to use the clean the table reinforcement learn skill, where it grabs the rag and cleans up the spot and then lets go. And then it jumps back to the VLA router where it can then choose the next task. That's how most of those are working these days. There are some caveats and some kind of mixed up approaches to that, but no one's doing like one generalist policy. There's a lot of research into it, but no one has done it to the point that I've seen it deployed on any of the like Android robots that you're seeing hit the news all the time. I think that this kind of approach with paired with the GRM could get to the point that maybe we're looking at more generalist robotic policies, which would be really exciting for me. Does that answer your question? Or
Yeah.
okay. Yes. Not just robotics, I think just anything in general with lots of steps. Because again, if we look at these results, this was 300 steps. That's really not a lot of time training. And you're getting a surprising result with 100% tool calling execution in a small model. That's impressive. I would love to see more statistics across larger models, but we don't have them. Yes.
300 steps is 300 search queries, it's questions and answers. Or is it
300 training steps.
batches?
Yeah, 300 training steps. So it's batches.
And those batches were like 500 later?
I don't remember off the top of my head, but it says in the appendix what they did for the training sizes. Something like that. It wasn't super large. Okay, other questions? Okay, any discussion about the paper in general or the idea? Like it's very simple. I know it starts out sounding really complicated, but it's really simple. Basically, it just boils down to when you have multiple turns in a reinforcement learning model, take the final turn score, multiply it by some decay relevance factor to decay the value as you go back, and then look at the turn value, figure out a score for that, and then just apply that back propagation separately. Really simple idea, but no one's done it before. Yes.
A bit more color around like how to find out the score.
Yes.
It's like a GRM or like
So they use their verifiers, which is one of my biggest problems with the paper. So like, okay, if you look at it, you call the tool, that's really easy to detect, right? You just have a little thing in your function that triggers whether or not you did it. Format, you run an XML formatter, pass, fail. Yeah. That problem with that is that that doesn't scale. That means now you now need engineering time to build out verifiers for everything. So there are typically other ways to do this. The reason I'm excited with the GRM is because it's basically a really powerful critic and an actor critic step. I'll explain that in a second, which fascinates me. Now, actor critic is, let's go back to GRPO. And this advantage function does not look like this for PPO, which is what you used for your car. What it looks like for this is essentially the resulting score, but the V of S is a separate model that you're training at the same time in PPO, which is called the critic model. And you are essentially training a critic model, sometimes with hidden information, sometimes with the same information as the actor model, is in an attempt to have it accurately say, in this state, you should be able to score this on average. And you learn that over time as well. That, of course, introduces its own problems, and which is why PPO is less efficient for, say, LLMs, where we could just say, okay, we have a group of responses with scores that we could go ahead and utilize. GRPO is better for LLM agents for that reason. Uh, but if you were to say create a really good critic, which is my proposal of using the GRM, this could technically be any value or any scoring rubric. And there's 1,000 ways you could possibly build that. And that's kind of up to you as the engineer understanding the domain of what you're building. Does that make sense?
Yeah.
Okay. Yes.
What does your intuition say about reinforcement learning applied to this sort of problem versus this supervised learning? Just train that a supervised model use the exact same data, and you have question answer pairs.
Yeah.
What, do you have any questions or thoughts about comparison of the two approaches?
I'm not sure if that would work well with an LLM agent, which is the focus of the paper. And that's, I think, why it worked so well here in terms of looking at LLM agents, because the LLM would just eventually learn to parrot back the supervised pairs. Whereas here you're utilizing it as try to teach it a way to reason about it, right? Because I don't care about that trivia. I care about the pattern that the trivia is forcing it to learn, which is call the tool, parse the tool, results, output the answer in this format.
Like process of discovery.
Yes. And this is what reinforcement learning is good at, and this is why reinforcement learning was key to reasoning models. And not just instruct-based, but also reasoning, is by teaching these models not to reproduce chain of thought, but rather to reward it to think longer and utilize that to produce the results that we were looking for, kind of takes that jump into more advanced models. Does that make sense?
Yeah. I'm just trying to understand why the generalization approach is like, you have an evaluation set, you have a validation set, you can't memorize and get a good score. And so, but it does have a lot of freedom to memorize. So, yeah, I'm just trying to wrap my head around it.
Yeah, it is kind of spooky. So reinforcement learning is, again, really unstable and can be really a big pain in the ass. But it can do things we can't do with your traditional deep learning or traditional machine learning feedback. And sometimes it's just spooky in how it works. Like you suddenly start to see these emergent behaviors pop out of almost nowhere, seemingly, and in such ways that you can't really fathom how we got there from this particular prior model, but somewhere in the math it works out. Reasoning models very much does that kind of spookiness to me, is like you're seeing this emergent behavior of reasoning despite there being no direct like way to reward it other than just think longer and some reinforcement learning algorithm added to it. So it's interesting. I don't know all the answers to that yet. All right. Any other questions? Any other commentary on the paper? Thoughts about it? What's that? Yes. Do you know what a bandit is? It's a slot machine. Yeah. So it's the name for a slot machine is a one-armed bandit because you pull it down and steals your money. Uh, in reinforcement learning, it's very connected to game theory. A lot of older MD Markov decision processes and a lot of algorithms basically talk about the bandit problem in just terms of you have a certain output. There is an optimal strategy that occurs when you try to pull the lever. What is the transition function? How does this work? It's a way to look at stochastic problems. Uh, they are bringing it up because LLM agents are stochastic problems. And by saying, okay, yeah, LLM agent calls individually per turn is a Markov decision process. They're basically referencing the bandit problem. And it's just a piece of reinforcement learning lore, I guess you could say, that they're basically referring to.
Like learning the transition.
Yes.
Or the probability. Hit the jackpot.
Yes. Any other questions? Okay, well, we'll end that there. Thank you very much for coming out tonight. I'm going to take 1 second to shut down the video and make sure